Unit 2, Where Am I? Video review for Honors Chemistry. You can access this review and this video at srhschem.wikispaces.com or on YouTube channel LEFFELlabs. First question asks us to identify an unknown substance to determine if it is a metal or a non-metal. So explain the steps to measure 3 different properties of the substance in an experiment that will help the student identify the sample. So there's 5 possible properties to test. We could test appearance, conductivity, malleability, reaction with hydrochloric acid, and melting point. So to test appearance, we need to observe the sample, and we are specifically looking for luster. Is it shiny or dull? The color, the state of matter. Is it a solid, a liquid, or a gas? So we can just observe and determine a lot of information about the sample just from looking at it. The next test is conductivity. So you'll use a conductivity tester to test the sample. So here I have a hunk of calcium, and I'm just going to take my conductivity tester and place the copper leads onto the sample. And what I'm looking for is how brightly the lights come on. So if there's no lights at all, it's not a conductor. If there are dim lights, we have some conduction. We call this a semiconductor. And if the lights come on nice and bright, like it does for our sample here, it means that it is a good conductor. Next test is malleability. So in malleability test, we are going to strike the sample with a hammer, and we're going to be careful not to hurt ourselves or break anything. And what we're looking for is we're looking to see if the substance is malleable. We could hammer it or shape it into a sheet. Malleable, another name for a hammer is a mallet. So we're looking for something that we can shape with a hammer. Similar to that is ductile. So ductile simply means that it could be made into a wire. The opposite of malleable and ductile is going to be something that is brittle, something that shatters when you hit it. So the two terms, malleable and ductile, are very similar. If something is malleable, it's also usually going to be ductile. So here we have a copper bowl that was hammered into that shape, and we have some copper wire. Next test is reaction with hydrochloric acid. So we need to take a small piece of the sample, which is convenient because we were just hitting it with a hammer, so you might have some small pieces of it ready to go. And we're going to want to put that into a spot plate and see if it reacts with hydrochloric acid. So we can drip some 1 molar hydrochloric acid on top of the sample. So in this picture, we've got some zinc in a test tube with some hydrochloric acid, and we can see a pretty vigorous reaction occurring here. So there's fizzing, there's some vaporizing. The bubbles that are being given off are actually hydrogen gas. And if you felt this test tube, you would feel heat being evolved or being given off by this reaction. Melting point, you just have to heat the sample until it melts, but this can require very, very high temperatures, so it can't be done in the classroom. For example, iron metal melts at 2800 degrees Fahrenheit. There are some metals that are going to be lower, like gallium melts at around 85 degrees Fahrenheit, just below body temperature. But usually this is going to require really high temperatures. So you'll just need to heat it until it melts and record that temperature. So you could have some high tolerance temperature probe or maybe one of those infrared thermometers, but it does need very high temperatures. So what materials are going to be needed for this experiment? So we'll need a sample to test, so an unknown element sample. We'll need a conductivity tester so we can test the conductivity. We will need a hammer so we can test the malleability. We'll need a spot plate and 1 molar hydrochloric acid solution. So these 2 things will allow us to test the reaction with acid. And then if we want to test the melting point, we're going to need something that's going to get hot enough to melt the sample, as well as some way to measure those very high temperatures. Next, create a data table of the measured properties. So here's all 5. So, you just have your sample, and then each test can be its own column. And then in this column, you can put all of your observations. So, appearance, you can write if it's shiny or if it's dull. Malleability, you could say that it is difficult to shape or it doesn't conduct. You saw no reaction with acid, etc. Next question, complete the table about the periodic table. So this is just knowing the family names and where to find them on the table of elements. So first we have the alkali metals. That's going to be group number 1. So the first column, our alkali metals are going to be things like lithium, potassium, sodium. These guys are all going to be very reactive. We have to store them under oil because they'll react with moisture in the air. So just highly, highly reactive metals. Next, we have the alkali earth metals in group number 2. So in the next column, these are going to be things like beryllium, magnesium, calcium. All of these are going to be very similar to the alkali metals, but just a little bit less reactive. All of their properties are similar, but a little bit less. So alkali metals are very, very soft. Alkali earth metals are still soft, but they're a little bit harder. Next, we have examples of copper, silver, palladium. These are going to be the transition metals. So you find these as that middle block. It's that D block in the middle of the table of elements. So group 3 to 5 column or 3 to 12, columns 3 to 12 are going to be our transition metals. Halogens are group number 17, so almost all the way over at the opposite end of the table of elements. And these are going to be things like fluorine, chlorine, bromine. These are also highly reactive, and halogens love to react with alkali metals. So we see a lot of compounds like sodium chloride, potassium bromide. These compounds typically form between halogen and alkali metals. Next, the last column, group number 18. These are our noble gases. These are helium, neon, argon, all of that column 18. These are all gases. They are non-reactive. They have stable, complete valence shell electron configurations, which just means that they don't react with any of the other gases. Next question is to color code table of elements to show the metals, nonmetals, and metalloids. So the key thing to look for here is the separation line. So that thick line dictates where all of the metalloids are. Now the only exception, everything that touches it is a metalloid except for aluminum. But that shouldn't be too hard to remember because you've experienced aluminum, you've seen aluminum foil, you know that that's a metal. So the things that touch the line, except for aluminum, are going to be our metalloids. The metals are going to be to the left of the metalloid. The exception, of course, being hydrogen up there in group 1 in that first spot. But everything else is pretty much a metal. That's over there to the left of the metalloids. And then to the right of the metalloids is where we get the nonmetals. An unknown sample is brittle, dull, and it does not conduct electricity. So which groups, which columns could it belong to? So the fact that it's brittle and dull and does not conduct, that tells me that it's a nonmetal. So that pretty much eliminates most of the table of elements. In addition, the fact that it's brittle, it must be a solid. So all I'm looking for is solid nonmetals. So group 14 has carbon in it. That's the only nonmetal, and it is a solid, so it could be carbon. In group 15, we have phosphorus, which is a solid, so it can't be nitrogen because that's a gas. So phosphorus is the only option in group 15. In group 16 could be sulfur or selenium. Those are both solids. Oxygen, of course, being a gas, so it can't be brittle. And then in group 17, iodide is also a solid. So it's not going to be fluorine, chlorine, or bromine because those are all gases. Number 5, what do the noble gases have in common? So They're all non-reactive gases, and they're all in column 18, but what makes them so similar has to do with the electron configuration. So all of the noble gases have a stable valence shell electron configuration. So for hydrogen, the first energy level can only ever hold 2 electrons. So hydrogen has a stable electron configuration because its outermost energy level, the first energy level, is full. It has 2 valence electrons. Neon, the second energy level, can hold up to 8 valence electrons. So neon has 8. Argon, in our third energy level, we have 8. And krypton, we also have 8. So there's 2 in the S and 6 in the P, so that makes a total of 8. So these all have these 8 valence, that full octet. They're all stable. Now the exception being helium, but it still has that full valence shell. It's just that the first energy level only holds 2 valence electrons. Rows are the same as series and periods. I remember that because row, series, and period are all at the end of the alphabet. And columns are going to be the same thing as families and groups. And I remember that because column, family, and group are both at the beginning of the alphabet. So the next one, number 7, is asking us to analyze the trends. So the best way to do this is to understand what shielding and nuclear charge are, and then to apply these concepts to the different terms. So here we have francium with all of its energy levels. Francium has 87 protons, so plus 87 is the charge of our nucleus. And 2 electrons, 8 electrons, etc., etc. So here's all of the energy levels. And in the last energy level, that green electron is the valence electron for francium. So that's that 7s1 electron, that 1 valence electron. Over here, we're going to compare it to fluorine. So fluorine only has 2 energy levels. It's in the second row of the table of elements, and it's got a total of 9 protons. So 2 electrons in the first energy level, 7 in the second energy level, and we're going to consider that 1 green valence electron there. So first, let's consider the green valence electron on francium. So that's all the way out in the outermost energy level. So these inner red electrons are shielding, they're blocking the green electron from the nucleus. So we have all these layers of electrons that are blocking the outermost electron from the nucleus. Now, francium has 87 protons, so the nucleus has a plus 87 charge. But there are 86 inner electrons between the green valence electron and that nucleus. So those 86 inner electrons have a charge of minus 86, and they're blocking the green valence electron. So these inner electrons, these shielding electrons, actually cancel out the charge of the nucleus. So the effective charge, what the green electron actually feels, is only going to be plus 1. So we're talking about a fairly weak attraction there. Now let's consider the green electron on fluorine. So this is in the second energy level, so the only shielding electrons are the 2 that are in that first energy level. So there's only 2 shielding electrons blocking the nucleus from the green valence electron. Fluorine has 9 protons, giving the nucleus a plus 9 charge. And just like with francium, those inner electrons are going to cancel out the charge of the nucleus. But this time, we've only got 2 inner electrons. So the effective charge that the green electron actually feels is plus 7. So we see for fluorine, we're going to have a much stronger attraction between that valence electron and the nucleus because the nucleus is so much more positive. So as we go across, we're getting more protons, so that attraction between the electrons and the nucleus is getting stronger as the nucleus becomes more positive. As we go down a column, we're getting more and more energy levels. So we get more and more of those shielding electrons, and that's going to cause the attraction between the electrons and the nucleus to decrease. So metallic character. This is just going to be how much an element behaves like a metal. And metals are metals because they lose electrons. So basically, my metallic character is going to be higher. It's going to behave more like a metal the easier it is to lose an electron. So we see as we go down a column, we get more metallic character, and as we go across a row, we get less metallic character. So metals easily give up electrons. And as we are moving across, those atoms are getting more and more positive in their nucleus. So those electrons are moving closer and closer to the nucleus. So it's much harder to remove that electron when that attraction is strong. So these are going to behave less like metals. As we go down, we're getting more and more layers of electrons. So more and more shielding, weaker and weaker attraction. The atoms are getting larger. It's easier to pull away an electron. So the most metallic element between fluorine and francium, these are kind of our two extremes. The most metallic is going to be francium because it has the most energy levels, the most shielding. So we end up with easier to lose electrons. Atomic radius. So atomic radius is the distance from the center of the nucleus to the edge of the electron cloud. So it's just the radius of the atom. We see that as we go down a column, that the size of the atom is going to generally increase. And as we go across a row, the size is generally going to decrease. We'll get smaller. So this is why. As we go across, we're adding more and more protons. The atomic number is increasing. So the attraction between the electron and the nucleus is going to get stronger. So the electrons move in closer because they're more attracted to the nucleus. So the atom gets smaller. As we go down a column, however, we're getting more and more layers of electrons, more and more energy levels. So that attraction is getting weaker, and the electrons are not going to be held quite so close to the nucleus because of that weaker attraction. So the atoms get bigger. So between fluorine and francium, we're going to go with the one with the most energy levels, and that's going to be francium. Ionization energy. So ion is a charged particle, and that tion ending means process. So we're looking at the process of making a charged particle. So the way we do this with atoms is to pluck away an electron. So we're trying to remove an electron from an atom in order to form an ion. So as we go down a column, it's easier and easier to remove an electron. So we need less ionization energy in order to do that. Whenever it's easier, we need less energy. So as we go down, that attraction gets weaker and our ionization energy decreases. As we go across, the electrons are harder to remove from small atoms because they are held closer to the nucleus. So we see that nuclear charge increasing. The nucleus is more and more positive as we add protons. So the electrons are more attractive, they move in closer, and it's going to be harder to pull away, to remove one of those electrons. So ionization energy is going to increase as we go across. As we go down, those atoms are getting bigger because there's weaker attraction, so it's easier to rip away an electron, so I don't need as much ionization energy to achieve that. So the highest ionization energy is going to be the atom which has the strongest attraction between electrons and protons in the nucleus. So that's going to be fluorine with its minimal amount of shielding and lots of protons. Energy levels. So the energy levels roughly correspond to the rows or the periods. So we have row 1 is energy level 1, 2, 3, 4, 5, 6, 7, and so on and so forth. So as we go across, each row is an energy level, which means that the energy level is constant. So anything in energy level 2, anything in row 2 is going to have the same number of energy levels. Now if we go down a column, each row is adding an energy level. So as we move down, we get more and more energy levels, all the way down to francium, which has 7. Valence electrons. So here's the trick. Everything in column 1 has 1 valence electron. Column 2 all has 2. 3 has 3 valence electrons, so on and so forth. This little shortcut rule doesn't apply for the transition metals in the middle, but it's a quick way to tell the number of valence electrons. So everything in the noble gas column has 8, the halogens all have 7, and so on. So as you go across, you're getting more and more valence electrons because we're adding more electrons. So lithium, for example, is 1s2, 2s1, so that's 1 valence electron. And then right next to lithium, at atomic number 4, is beryllium, and this has 2s2, which means its valence shell has 2 valence electrons. And if we went over to boron, we would see 3 valence electrons, so on and so forth. So as we go across a row, we're getting more and more valence electrons. As we go down a row, however, it's going to be constant. Every family or group has the same valence electron configuration. So lithium has 1 valence electron, sodium has 1 valence electron, and so on. So electronegativity. This is how well an atom attracts electron whenever it's in a compound. So if you have 2 atoms in a compound and one of them is better at attracting electrons, that one is going to have higher electronegativity. So as we go across, we're getting more and more protons. So that nucleus is more and more positive. There's a stronger attraction. So it's better at attracting. We get higher electronegativity as we move across a row. As we go down a column, again, we're getting more and more shielding, more energy levels, more layers of electrons, means that this attraction is weak and the electrons are not held quite as close to the nucleus. So this means electronegativity decreases as you go down a column. So between our 2 extremes, the highest electronegativity, or the most attractive atom when in a compound for electrons, is going to be fluorine. The shielding effect. It is the blocking of the valence electrons by the inner electrons from the nucleus. So this reduces the attraction of the valence electron to the nucleus, the more shielding we have. So as we go across a row, shielding is going to remain constant because the energy level is going to remain constant. We also see that as we add each additional electron, we're also adding additional protons. So that ratio of electron to proton remains constant as we go across a column. As we go down, however, we're getting more and more energy levels. So there's more and more of those inner electrons that are blocking the nucleus from the outer electrons. So as we go down, we see that the shielding effect is going to increase. So this also applies for largest radius because the one with the fewest energy levels is going to be smallest. So the largest radius is going to be francium. Reactivity. So metals, as we go across, the reactivity decreases, and as we go down, it increases. For nonmetals, we see the opposite. As we go across, the nonmetals become more reactive. So the halogens, the nonmetals in column 17, those are all very reactive. As we go down the column, we see that the reactivity decreases. And this has to do with how metals and nonmetals react. So metals react by losing an electron. So as you go across a row, it's harder and harder to lose electrons because that attraction increases. So the reactivity becomes lower. But as you go down, you're getting more and more layers of electrons. It's easier to lose one, so the reactivity goes up for metals. So the most reactive of the metals is going to be francium. For nonmetals, they react by gaining electrons. So the more attractive a nucleus is to electrons, the more reactive a nonmetal is going to be. So as we go across, we're getting more protons. The nucleus is more attractive. So because it's easier to gain electrons, it becomes more reactive. As we go down, however, we're getting those energy levels that are increasing. We're getting more shielding. So the reactivity is going to decrease because it's harder to gain an electron for those atoms. The most reactive nonmetal is going to be fluorine. Number 8 is about periodic trends. So of our choices, lithium, boron, carbon, or fluorine, which is going to be the smallest atomic radius. So atomic radius is just the size of an atom. And in this particular problem, shielding is constant. We're all in the same row. We have the same number of energy levels. But as we go across the row, we are getting more protons. So this means the attraction between the electrons in the nucleus is increasing because the nucleus is more positive. So those electrons are going to move in closer and we're going to get a smaller radius. So of my choices here, the smallest atomic radius is going to be fluorine because it has the most protons in that row. Next, strongest metallic properties. So we have oxygen, selenium, tellurium, and polonium. So we're looking for metallic properties. So which one is going to be easiest to lose an electron? So we're just looking for the one that's going to have the most energy levels. So as you go down, we get more energy levels, we get more shielding, and the attraction becomes weaker. So as that attraction becomes weaker, it becomes easier and easier to lose electrons. So of these choices, the most metallic is going to be PO. And this is also the only one of the choices that is a metalloid too, so that's going to be more metallic than the non-metal choices. So now we're looking at lowest ionization energy, and we're comparing beryllium, oxygen, potassium, and bromine. So ionization energy is how much energy I need to make an ion. So how much energy do I need to rip away an electron and ionize the atom? The harder it is to rip away that electron, the more ionization energy is needed to accomplish that. So, whichever one has less energy levels, there's going to be less shielding. So the attraction between the nucleus and electron would be strong, and it would be hard to lose electrons. So by that logic, since we're looking for the lowest ionization energy, the easiest to rip away an electron, we can eliminate beryllium and oxygen because those only have 2 energy levels, whereas potassium and bromine have more energy levels, so it would be easier to take away an electron. More protons also means a stronger attraction, and it makes it harder to lose electrons. So between potassium and bromine, I'm looking for the one that has the fewest protons, so the weakest attraction, easiest to remove an electron. So the lowest ionization energy of our choices here is going to be potassium. The next question is about the formation of ions. So metals are going to tend to lose electrons and they're going to form cations. So here's a sodium atom. This is a metal. And whenever we form a sodium cation, it becomes Na plus 1. So it only has 10 electrons. We've lost an electron. So to become a cation, which is positive, the sodium had to lose an electron, making the radius of the ion smaller than the radius of the atom. Nonmetals, however, tend to gain electrons and form anions. So here I have chlorine, which is a nonmetal, and it's going to tend to gain an electron, making its charge -1. So become an anion, which is negative, the chlorine atom had to gain an electron, which means the chlorine ion, the ionic radius, is going to be larger than the atomic radius because there's more electrons. Last question is to compare the metals, nonmetals, and metalloids. So for metals, we're looking for things that are silvery, that are shiny. The exceptions, of course, being copper and gold, which are copper and gold colors. They're not silvery. Conductivity of metals is going to be good, and that's both heat and electricity. The melting point is going to tend to be high. There are some that are on the lower end, but they're all going to be pretty high. And they're going to be very malleable, so I can easily shape them. And uses for these are going to be pipes, wires, and jewelry. So all of these are based on the properties of metals. It doesn't make sense to make wires out of something that doesn't conduct. So since metals are good conductors, that's why they tend to be made into wires. The metalloids. So these guys can kind of be in between. They can be shiny or dull. They're usually going to be semiconductors, so a lot of uses there in computers and technology. The melting point is going to be a little bit lower than metals, but still higher than nonmetals. The malleability, they can be malleable or brittle. So, for example, silicon is very brittle. And these are used a lot for technology and computer chips. So here we have nonmetals, which can be many different colors, but they're going to be dull. So there's sulfur, which is yellow. Phosphorus has a red color. There's carbon. So carbon can be, there's clear like a diamond, or it could be dark black like graphite. The conductivity of these is going to be little to none, and their melting points are going to be comparatively low to the metals. Malleability is going to be poor. They're going to be brittle. And uses for these, match heads are made of phosphorus. Carbon is the element of life, so very important there. So some tips. For the trend problems, and this is the bulk of the problems that are on the test, figure out what the term means. So know what electronegativity is. Know what atomic radius is. And then determine which element is going to have the highest in that term. So is it going to be francium or is it going to be fluorine? By applying those concepts of shielding and nuclear charge. So by figuring out how that attraction changes between the electrons and the nucleus. And then you're going to look for the element that's either closest or furthest away, depending on the question. So like the highest electronegativity is going to be fluorine because it has the least shielding and the most positive nucleus. So if a question is asking which of the following has highest electronegativity, I just want to pick whichever one is closest to fluorine. And you should definitely write on your table of elements. As you're doing these problems, highlight them, see where they are, how close they are together. Those are all things that can help you.